Hello, students. This is your professor, Dr. Mink. You might have just finished part one of chapter 5. This is part 2. We will pick it up with indirect addressing mode, and it is absolutely fine if you just finished part 1 and you flow right into this. So let's get started. The next addressing mode we'll cover is indirect addressing mode. Remember, with PC relative mode, we can only address data within 256 words of the instruction. That's kind of limiting. So how do we access the rest of the memory? I always say that PC relative mode has a leash. And in order to get unleashed, if we need to go further than 256 words or memory addresses, words and memory addresses is the same thing. A word is a memory address. In this case, it's a 16-bit word of memory. So the first solution is to read the address from a memory location, then load or store to that address. The first address is generated from the program counter in the instruction register, kind of like PC relative addressing. Then the content of that address is used as a target for load store. I know that sounds a little convoluted. There probably could be a better, more comprehensive explanation, but don't worry about it because guess what's coming next? Another demonstration video. Hang in there. So, as I mentioned, we're going to take this program, and I've already put it in Canvas so you can access it there. It's called LDI STI. We're going to take this program, we're going to run it through the assembly process. But before we do, I'd like to go over something new. If you're looking at this, you might be thinking, what's that A.fill X3016? Okay, fill allocates a single word of memory with the value, in that case it's an hexadecimal value, 3016. And A is a label. I know, lots of moving parts here, but it's the easiest way to do this, to put a label on that particular memory address. So the first thing that we see after the origin statement is 3016 in binary. And you could look at that and see it. So that's a piece of data. And then we AND R6 with 0 and store it back in R6. We add 1 to R6, which is 0, and add it to R6, or store it in R6, so 1. And then we add negative 16 to R6, which holds 1. So we're going to ultimately wind up with negative 15 again in R6. Then we have store indirect, STI. Store means to move from a register out into memory. And A is used indirectly to specify the address. A actually generates an offset, a 9-bit offset, automatically. By putting A there, the first pass of the assembler, notice it takes 2 passes, and I know we're getting way ahead of ourselves, but it's hard to avoid introducing this at this point. The first pass of the assembler resolves all labels into actual offsets and hexadecimal memory addresses, because in machine language, there are no labels. There are no mnemonics. There's just zeros and ones. That's all we have. So if you look at the corresponding machine language instructions generated by STI, R6A, you'll see 1011, which is the opcode for STI. And then you'll see 110, which is R6. And then you'll see, and I have it highlighted here, the 9-bit offset. So what is that 9-bit offset? Well, that gets added to the program counter to identify the location of a full hex 16-bit binary address, and that is 3016 in hex. So what is that number that's highlighted 111111011? Well, if you flip all the bits, right, everything at the beginning becomes zeros, and then your first significant bit is 100, and then add 1, it's 101. 1, 2, and 4, that's -5. So when this store indirect command is executed, the program counter will actually be pointing to the address of LDI when it actually calculates the offset. So then count back -5. 1, 2, 3, 4, 5, and that gets us to the fill. That gets us to 3016, and that's the address that'll be used to store the contents of R6 in. LDI also uses A, but if you notice, LDI has a 9-bit offset that is 1 less or 1 more negative, right? That's going to come out to -6 because A, when the program counter is added to that offset, A is 1 further away. You really need to stop, pause, and take a look at this. And if you don't understand how this is being calculated, you can't just say, I'll figure it out later. You got to ask me. You got to seek help. This is very cryptic. I get it. I've done this 1,000 times, more than 1,000 times. But this is really important that you understand how indirect addressing works, because I will have to assess you on this, and I want you to know it. So I'll gladly help you. Come to my office hours or ask me for additional one-on-one help, or 2 or 3 of you get together and we'll discuss it. So now I'm going to run this and I'll show you how it actually works. So here we are. I went to Canvas, copied the code into this. I'll save it. LDI, STI, I'm sure I already have that, yeah. Let's do this because I don't know if I've made any changes. I don't know if it'll allow me to put that in there. Yeah, it is. So run the assembler. Light up the simulator. Reinitialize. There's the object code. And there's A. And it tries to resolve it. This is one particular area where the simulator is not great. It thinks that's an instruction. It's not an instruction. Okay. So here's the 1 to R6. Here's -16. Add it to R6. And now STI R6A. Okay. It's going to go back to A, 3016. Now watch. Now I need to scroll down so you can see this. There's 3016, and there's where we stored, was it -15? And we come back. Now we're going to load in directly into R7, A, and there it is. I don't mean to sound like a broken record, and most of you probably don't even know what a record is, but something old people say. I don't mean to keep on repeating myself, but you really need to take the time, download these files, run them in the, because what happens is I wind up with students in this class, and I've taught it for years, Years. I teach 3 or 4 sections a year. Yes, for years. So quite a few sections. And students are lost by the time they're required to write some programs of significance. And it's because they didn't spend the time downloading these files. And if you're having a problem, I'm pretty accessible, especially now in this all online mode. Ping me and we'll get together, show up at my office hours. It might only take me a few minutes to explain this. What you need to do is, if you're having problems, just send me an email saying this is what I'm having a problem with, so I could prepare maybe a little demo for you. And I need to come to your office hours, or I need to get together, and we'll work through it. Really, I want you to feel supported in this environment, but I need your help. Here's a data path for LDI. You'll see the memory address register needs to get the sign extended, offset, and add it to the program counter. Then the memory address register needs to go to that location, which was a label, which generated an offset, and then use that value to calculate the actual address in memory where we're going to load from. And then it comes a memory data register, and then it's stored into the destination register. I think at this point in time, when we're talking about complementary store and load indirect type commands, I don't need to go. It's just backwards. You can follow the data path. If you have any questions, let me know. I don't want these lectures to be, overwhelmingly long, because I know students get bored. So take a look at it. If you have any questions, let me know. So in the previous demo, I used an assembler directive .fill. These all start with a period, and they have different purposes. We've already been using .origin, O-R-I-G, which specifies where to start placing things in memory. So up till now, we've only used hex 3000, but we will, trust me, we will use other origin statements. And specifies the end of the program. .fill is used to declare a memory location, and it's followed by a value, hex or decimal, X or pound, that will place that value in the next available memory location. Block W, BLKW, is followed by a hex or decimal value, but that declares a group of empty memory locations, an array, if you will. If you put block W pound 10, or I think you can just put 10, it'll declare 10 continuous or adjacent empty memory locations, and they're all initialized to 0. And then string Z declares a group of characters in memory, a string. And just leave string on the sideline for now. We're going to need string Z when we do I/O, but I don't want to overwhelm you with too much information. We're not going to use block W for a while either. So fill is the one that's most pertinent. Solution number 2 to being leashed with the program counter plus offset mode, 256 plus or minus, is base plus offset addressing mode. So we're going to use a register to generate a full 16-bit address, and we can also add an offset to that. Obviously, we're going to take a look next. Here we have the syntax for LDR. Opcode is 0110. Bits 9, 10, and 11 specify the address of the destination register that we're loading into. And then bits 6, 7, and 8 are the base register, which will hold a full 16-bit memory address. And we can also add an offset to the address. It's a 6-bit 2's complement sign extended offset. Here's a data path for LDR. If the 6-bit offset is used, that's added to the value in the base register to calculate the address of the memory address that gets loaded in the memory address register, and then the contents of that gets loaded in the memory data register and then stored in the destination register. STR works the same way, only backwards. We take the sign extended 6-bit offset if it's used and add it to the full 16-bit memory address in the base register. Those two get added together and loaded into the memory address register, which then specifies the location that we're going to store the value from the source register. So the source register value gets loaded in the memory data register, which then gets copied or stored in the memory address in the memory address register. The last load command we're going to cover is LEA, load effective address. It computes the address similar to PC relative and stores a result in a register. The address is stored in a register, not the contents of the memory location. That's how it differs from the other load commands. And almost always you use a label with load effective address. I can't recall a time. I mean, you don't have to, but it's so convenient if you're writing the code in assembly and then converting to machine language to use a label. But it doesn't store the contents of the label or the targeted address. It stores just the address. Here's a data path for the LEA, and it does have a 9-bit offset that gets sign extended and added to the program counter. However, the targeted address is not used to get the contents of that address. It's used to just write the value to the register. And this is very useful when we're processing an array of data and we label the first element in the array with a label. Here is your first assignment with regard to the LC3. I'd like you to reverse engineer this machine language program. Notice it starts at 30F6, and you can see the opcode for each of the instructions. I want you to, and this is in the timeline as an assignment, I want you to take this program, decode all of the instructions. I need you to write a fully coded assembly language source code file, .asm file, so that when it's assembled, it generates this program. Next up, we have the control instructions. These instructions are used to alter the sequence, the flow of execution from linear to nonlinear by changing the program counter. And if you look really closely, if you've been paying attention and you look really closely at the process, the program counter actually gets changed twice. It gets a +1 during fetch before the instruction is even evaluated or decoded. And then it gets reassigned by the control instruction. We have a conditional branch, which is taken when a specified condition is true. And if that condition is true, the signed offset in the branch instruction is added to the program counter to yield your new program counter value. If the condition is not true, the PC is not changed and it points to the next sequential instruction. An unconditional branch or a jump always changes the program counter. Now a trap, which we're going to get to in significant detail, it's a topic unto itself later in the course. A trap executes an operating system service routine. And an operating system service routine looks like a subroutine, and we're going to get to subroutines also. But the trap, the call to the trap routine causes the program counter to assume a value in the operating system, in that reserved space. So you can't just jump there with a branch or a jump. You need to use a trap routine. And we'll talk about that entire process, but it is one of the control instructions, because in control instruction, because it does deviate from, or causes the machine to deviate from a sequential +1, +1, +1 program counter flow of control. The LC3 has 3 condition code registers: N, negative, Z, 0, and P positive. And these are set by any instruction that writes a value to a register. So going back to the instruction set, any instruction that has a destination register in its syntax will set the condition code. Now, condition codes are set all the time and never used. So it's not a matter of, oh my God, I set a condition code, I have to use it. No, you would set this up prior to the branch or the control instruction that's going to have a conditional branch, so that you'd be using the condition code, or you'd be setting up the condition code to get the result that you want. Exactly one of these condition codes is set at all times. You always have either NZP. Whether you're using that NZ or P, that's up to the programmer. The branch instruction specifies one or more conditions when, if true, the program counter gets reassigned. It actually gets reassigned a second time because, remember, the program counter always gets +1 during fetch. And that's before the opcode is decoded, any operands are evaluated, anything else happens. Before we even know, or the system even knows what the instruction is, the program counter is already +1. So, and it uses PC relative addressing, has a 9-bit offset, which allows us to go plus or minus 256 words of the branch instruction. And if the branch is not taken, the program counter is already pointing to the next instruction, so we continue on with a linear flow of control. This is the data flow diagram for the branch instruction. Obviously, the opcode is 0, 0, 0, 0. Then bits 9, 10, and 11 specify the conditions under which the branch will be taken. The offset in bits 0 through 8 will be added to the program counter if. So if you have 1, 1, 1 in bits 9, 10, and 11, it then becomes an unconditional branch. It is going to branch if the condition code is negative, if it's 0, or it's positive. But if you have 1 in N, 0 in Z, 0 in positive, it's only going to branch, it's only going to add that program counter offset if the condition code is negative when this instruction is encountered. And the data flow diagram shows it takes bits 11:9, the NZP condition codes, checks the logic, and determines whether or not it's taken. If it is taken, then its sign extends the offset, adds it to the program counter, and it reassigns the program counter. This doesn't move any data, it doesn't do any arithmetic or logic, it just reassigns the program counter, thus causing a branch or a jump or a nonlinear flow of control. Now let's take a look at how we can use a branch instruction to create a loop that will compute the sum of an array of 12 integers. Now there's a lot of moving parts on this one, so stay focused here. First, because we haven't covered I/O yet, we're going to need to put the data in at 3100. And in order to do that without entering it or soliciting it from a file, because we haven't gotten to any I/O yet, we're going to need to manually put that data in to memory. And I'll show you how to do that next. Here I have a file. Well, we're going to create a file out of this. I have a program that we're going to save as an ASM. All it does is it has an origin statement at hex 3100, which is going to be the starting address of an array of 12 integers. And just so we can easily identify the integers, I placed 12 fill commands. Remember, fill declares and initializes a single word or memory address with the whatever value is there. So we're going to fill a decimal 10, then fill decimal 20, 30, 40, 50, and this data will begin at 3100. And we put the end statement. So next I'll show you, I'm going to take this and I'm going to copy this to my clipboard. And then I'll show you how to get this. This will be a two-part video demo. I'll show you how to get this into the LC3. First step is I put that entire file into the LC3 editor. I save it. I think I saved it as something like fill12.asm. And then I assemble it. Oh, I'm missing looks like there must be missing, yeah, I'm sorry, one of the fill commands is missing the dot. There you go. I got an error because it didn't recognize it without the dot. Sorry about that. So there it is. So now let's go to the simulator and I'll reinitialize the machine and I'll load fill12.obj. And there it is. At 3100, there's 10, there's 11, 12, no, I'm sorry, 10, 20, 20, 30, 40, 50, 60, up to 120, I believe was the number. So there's the data in there. Next, I'm going to stop this video and I'm going to show you the program we're going to use to implement a loop. And what it's going to do, it's going to set a pointer to 3100. It's going to load the value at 3100 into a register. It will add that to an accumulator variable or accumulator register. It will increment the pointer so it's pointing at 3101, load, boom, boom, and it will keep on doing that until we're going to use a counter to set the condition codes. So let's pause here. I'm going to stop here and I'll set up the next demo. But I'm going to leave the machine, and you should do the same. I'm going to leave the machine like this. This is the program we're going to use to add those 12 numbers stored. I'll walk through it one instruction at a time, but let me be crystal clear. You need to load this program, assemble it, use the data I've given you, and run it and understand how this is going to work. I don't care how busy you are. This is a critical junction in this course. If you try to fake your way through this part, it's going to be a train wreck. You need to we're early in the process here. You need to understand how to run programs in the LC3 and understand all of these commands in this program. So, sorry, but I needed to put that out there because I've seen too many times students kind of fake their way through this. I'm too busy. I'll figure this out later. And then it snowballs, and next thing you know, they're in my 240 class the following semester. So, and I don't want that to happen. So origin for this, because it's our program, hex 3000. LEA R1 with an offset of FF. Now just take a minute and think about how that works. I deliberately did not use a label, but think about how that works. How does that FF work together with a program counter offset to load the address 3100 into R1? Think about overflow. Think about adding F plus 1. What does that give you? A 0 with 1 overflow. Carry out. F plus 1, 0 with 1 carry out. 0 plus 1, 1, 3 plus 0, 1, 3100. So then we're going to AND R3 and 0 and store it back in itself, just to set it to 0. Do the same with R2. And then we're going to add R2 and 12. Store it back in R2. This is going to be our counter. Then we encounter, no pun intended, we encounter our first branch, BRZ. This is a while loop. What will the condition code be the first time we encounter BRZ? Well, we just wrote a positive 12 to R2, so it'll be positive. So we won't take that branch. Then we're going to load register R1 with an offset of 0. What's R1 pointing to? R1's pointing to, or R1 has a pointer to 3100. So we're going to load the value pointed to by R1 into R4. And then we're going to add R4 to R3 and store it in R3. That is our accumulator variable. R3 is our accumulator. Then we're going to add 1 to R1. That's our counter. Oh, I'm sorry. That's our pointer. R1 will no longer point at 3100. After that, it will point at 3101. Then we're going to decrement R2, which is our counter. We're going to subtract 1 from it and write it back into R2. BRNZP, what is that? That's an unconditional branch. Where are we going to go? Right up to BRZ5. Count it. Okay, the condition code is still set. What did we write in R2 to set the condition code? 12 minus 1 is 11. 11's positive. We're not going to take that branch of 5. We're going to go load the contents, load the value pointed to by R1 into R4. That's going to be the value at 3100. Okay. Add it to the accumulator, increment the pointer, decrement the counter from 11 to 10, take the unconditional branch back to BRZ5, still positive. So we will continue to branch until what happens? until the counter goes to 0. This is a count-controlled loop. Here we are back where we ended the other demo. I still have my data here. I'll start a new assembly source code. My tabs always get a little bit off when I go from PowerPoint into here. So anyway, here's our program. We've already discussed it. Going to save it. I'll call it add 12 ints. I'm sure that's probably .asm. Oh, don't have an add 12 ints. And I'll assemble it. And let's run over to my simulator. Now, if you're not paying attention to this, or you paused it and went somewhere else, you are going to be totally lost. I've already loaded one file into the simulator. On top of that, I'm going to load a second, my add 12 ints. And it will set the program counter to 3000. My data is still down there at 3100. Now, I'm going to step into this program, step at a time. LEA R1, it resolved that value that I did the arithmetic for. So there's our pointer. We're clearing R3, we're clearing R2, we're adding 12. There's our counter. We got our counter. We have our pointer, and our accumulator is zeroed. Okay, we're going to load register the value pointed to by the address in R1 into R4. I believe it was a 10. There it is. There's the 10. And then we'll save that or add that to our accumulator. So there it is. Now we're going to increment the pointer. R1 has 3100. That's the beginning of the data. Now it has 3100. I'm sorry, 3101. We're going to decrement the counter, which is in R2. There it is. Subtract 1. Now 11. This is an unconditional branch. We're always going to come back up. There we are. We took our first branch. The condition code is still set at P, positive, because of that 11. BRZ, that's not going to be true. It's going to be false, so we're not going to take that branch, and we're going to start over. R1, now pointing to 3101. We're going to load that value into R4. We'll overwrite that 10. I think it's 20. There it is. Add it to the accumulator. There it is. Increment the counter. I'm sorry, increment the pointer. 3102. Decrement the counter. It'll go from 11 to 10. BRZ, it's still, condition code's still positive, so we're not going to take the second branch. And if we continue to go, it will load and then add all those values. Now I'm going to keep on going. All right, we're getting close. The counter is down to 1. I believe the last value is 120. So let's go. There it is. 120 gets loaded into R4. Then we're going to add it to the accumulator. 660, 120 should be 780, right? The pointer's really irrelevant at this point in time. Here's what happens. Watch. We're going to add R2, which is 1, and negative 1, and store it back into R2. Look at the condition code now. It's P. Watch what happens. It's now Z. This is unconditional, this branch. We're going to come back up. This is not unconditional. This branch which is the while loop, the conditions at the beginning of the body. Z, BRZ, go to 300A. Condition code is Z. Boom. We're now beyond the loop. We're outside of the loop. We've jumped over it. It's done. The accumulator has all those values in it. Now, I don't want to sound like a broken record, but you have to download these files. I'm giving them to you. You have to do this. You have to understand. You have to walk through this. Now, on to your assignment for the second part of Chapter 5. I'd like you to take this data, which is an array of values that terminates with a sentinel value. What is a sentinel value? It's a unique value. In this case, it's a negative value. And I'd like you to write a non-count controlled loop. If you submit a count controlled loop for this assignment, it is a 0. 0. Boom. If I open it, I could tell within about 4 seconds if it's a count controlled loop. Take the counter out of there, because I am going to have multiple files. One that has about 1,000 values in it. Like, let's just assume it's 1,027, or it might be 1,287, some unknown value. And you're going to just continue to sum all of the integers in that array until you encounter the negative value, the sentinel value. And also, I want this implemented as a do-while loop, which means you can only have one branch command in the program. Those are the criteria. Here's the data. I'll put it in the Canvas timeline. Of course, you can ask any questions you want, but do not submit a count-controlled loop. Got that? Raise your hand if you don't understand that. Good. I don't see any hands up. We're good. On the same page. One more control instruction that we're not going to use for a while. Jump is an unconditional branch, which means it's always taken. You might have noticed I coded an unconditional branch using BR. Jump is always taken. The target address is the contents of a register. Its address is in bits 6, 7, and 8. And it allows any target in address. I'm sorry, any targeted address. Jump has a brother or sister command, return. Return is simply a hard-coded jump R7. Bits 6, 7, and 8 are hard-coded as 1, 1, 1. So jump has a base register as its single operand. Return has nothing. And you'll see why return is a jump R7 when we get to traps and subroutines. R7 plays an important role in the linkage back, but I don't want to overwhelm you at this point in time because we haven't gotten to subroutines or trap routines, and we will cover them in great detail, and jump and return will become front and center during those lessons. The last control instruction, trap, which we will cover in very significant detail. There's an entire lecture on trap routines, and then we use trap routines all throughout the IO portion of the class. But trap calls is a control command that calls a service routine identified by an 8-bit trap vector. And the 8-bit trap vector is represented by a hexadecimal number. Remember, 1 bit of hex It's 4 bits of binary. So hex 23, which is the trap vector for input a character from the keyboard, actually comes out as 00100011. And that's 23 in hex. Hex 21, output a character to the monitor. Hex 25, halt the program, which stops the clock, stops the clock cycle from running, stops the program from going +1, +1, +1, +1, +1 with the counter. So we'll talk about how this works later in very significant detail, but it is included in the overview of the control instructions. And that, my friends, is the end of the second part of the lecture for Chapter 5. Hope you enjoyed it. We covered a very significant amount of material, lots of new concepts, some very cryptic concepts. So please do not hesitate to reach out to me if you need help on any of this. Now, don't watch this video and fast forward and then say I need you to explain all that. I've gone to great lengths, significant time investment to digitize everything I would do in the class. And I do need you to watch this video. You have the ability to rewind it, fast forward, watch sections over and over again before you come to me and ask for help. Thanks for watching. Have a great day.